Before I can start the next section, I have to deal with something called sigma notation. It's a technical device that's used to make adding a bunch of numbers easier, at least as far as the notation is concerned. So imagine I'm trying to add up all the numbers from all the whole numbers from 1 up to 100. So when you write something like this, I mean 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. The 3 dots in here means that we continue as has been had before and go all the way up until you get to 100. Well, we have a shorthand way of writing this, and it looks like this. I've used the letter K. I write K equals 1 to 100, and I use the letter K. What we have here is a notation that uses its own kind of a variable that increments by a whole unit each time. So let me explain what this means. K equals 1, and we have K equals 1. Then we add the next term and increment this to K equals 2. K equals 2. Add, then increment. K equals 3. Add, then increment. And you do it all the way up to 100. Let me do some examples to illustrate this notation. Basically, this tells you where to start and where to stop, and you fill in everything in between. So I have K equals 2 to 5 of the number K. So K is 2, then it's 3, then it's 4, and then it's 5. It doesn't have to start at any particular number. It can really start anywhere. The whole thing is, though, it's going to fill up the numbers at the ends and every whole number or integer in between. Suppose I had something like K equals -3 to 3, 5 to the K. That means you would start at K equals -1 and write 5 to the -3 plus. Then you would go to K equals -2, 5 to the -2 plus. Then K equals -1. And then K equals 0, so 5 to the 0. K equals 1, 5 to the 1. 5 squared plus 5 cubed. Let's see, 5 to the -3 is 1 over 125. 5 to the -2 is 1 over 25. 5 to the -1 is 1 over 5. 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25, and 5 cubed is 125. So let me add the whole numbers together and let me add the fractions together. The whole numbers add up to 156. And to add these all together, I'll need to get a common denominator. So I'll use 125 as the common denominator. Then if I add them together, I get 25 plus 5 is 30, 31. So I could write my answer as 156 and 31 over 125. All right, for this one, you see that I have K is going from 0 to 4, sine, and I have these numbers inside of here. The only variable is the K. So let me write it out in complete detail. We'll start with sine of, we'll have, when k is 0, you're going to get 2 times 0 plus 1 times pi over 2 plus sine of, and then k is going to go to 1, so 2 times 1 plus 1 times pi over 2 plus sine, now increment k equals 2, 2 times 2 plus 1 times pi over 2 plus sine, now increment k to 3, and then finally the last one is when k equals 4. So let's take a look at the first one. This is sine of pi over 2. The 2 times 0, of course, is 0. So I just get sine of pi over 2, and that's 1. And then here, 2 times 1 is 2, but I add 1, and I get sine of 3 pi over 2, and that's negative 1. Then I get sine of 5 pi over 2, which is positive 1. Sine of 7 pi over 2 is negative 1. And finally, sine of 9 pi over 2 is positive 1. So this ends up being 1. Let's do k equals 0 to 5 cosine of 2k pi. So that'll equal cosine of, start with k equals 0, cosine of 0 pi plus cosine of, now plug in k equal 1, so I'll have 2 pi plus cosine, then when k is 2, I'll have 4 pi plus cosine, I think you're getting the idea, cosine of 6 pi plus cosine of 8 pi plus cosine of 10 pi. And for even multiples of pi, cosine is 1, so I'll have 1, 1 plus 1 plus 1 plus 1 plus 1 plus 1 for a total of 6. Here's something you should recognize too. When I had 2k, all of my numbers were even. That's a way that you make numbers even, is to describe them as 2k. Look at the previous ones. 2k plus 1, and that supplied us with all odd numbers. I had 1, then 3, then 5, then 7. You get the idea. These are the ways you can specify just odds and then just evens. Sometimes I might not be able to come up with the formula right off the top. Suppose I have k equals 1 to 3 of k to the p. Don't know what p is, but then I can just write this as 1 to the p plus 2 to the p plus 3 to the p. And that's all there is. This is really all you can do because you don't know the value of p. So, as another example, use a sigma notation to rewrite each of the following. So we'll start off with just odd numbers, 1 plus 3 plus 5 plus, and then when I write dots, you got to remember this continues, so it goes through 7, 9, 11, blah, 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 until you get to 101. So how could you rewrite that using sigma notation? Well, there's your sigma right there. By the way, this is the capital Greek letter S. It looks like I want to do all odds, so I want to do what I did before, something like 2k plus 1 that will guarantee I'll do all odds so long as I start k off at 0. When I start k off at 0, I'll get for my first term a 1. So k equals 0. Now how far does it have to go to get 101? Well, you can kind of do this in your head. But if 2k plus 1 is supposed to be 101, so imagine in your head 2k plus 1 equals 101. Subtract 1 and you'll get 2k equals 100. So k would have to be 50. How about 5 plus 10 plus 15 plus ... plus 100. So now I'm going to 100 by 5s. This time I would start k equals 1 and write 5k. And then you'll start with 5, and then when k is 2 you'll get 10, when k is 3 you'll get 15, etc., etc. How high does it have to go? Well, 100 equals 5 times 20. How about 1/2 plus 2/3 plus 3/4 plus, and this goes all the way up to 99 over 100. So I think I'll start k at 1, and I'll probably put a k up here. I'll figure out if I start at k is 1, and that's the number that's up here, then it should go up to 99. And then how should I write it? You'll have k, but then this is 1 more every single time, so I can write k plus 1 down here. The letter is not important. I'll usually use a K or an I, but you can absolutely use any letter that you would want. Another common letter that's popular is the letter N. What if I do n equals 1 to 5, 1 plus n squared? So that means you're going to start with n equals 1. So you have 1 plus 1 squared plus 1 plus 2 squared. And I'm going to go all the way to 5 squared. 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared. This equals 2 plus 5 plus 10 plus, let's see, 4 squared 16 is 17 plus 17 plus then 26. And this adds up to 43, 53, 60. But any letter is allowed. Here's a case where p is being used. 2p plus p squared. Now, seeing what I did last time, I'm going to suppress all the complex details in here and simply write the number that results. So when p equals 1, I'm going to write 2 plus 1 is 3. And then when p equals 2, I get 4 plus 4 is 8. P is 3, I get 6 plus 9 is 15. P equals 4, I get 8 plus 16 is 24. P equals 5, I get 10 plus 25 is 35. P equals 6, I get 12 plus 36 is 48. Plus, and then the last one finally, 14 plus 49 is 63. By the way, I feel pretty good about what I just did, because if you look, the difference between 3 and 8 is 5. The difference between 8 and 15 is 7. The difference between 15 and 24 is 9. You see, these differences are going up in a regimented fashion. Then it goes up by 9. Then it goes up by 9, by 11, by 13, by 15. So our answer is, let's see, 11, 26, 50, 85, 133, 196. Now what I really want to do in this section is develop a few formulas that we'll use for the next time. Let me separate what I've done before. Let C be a constant. Then what does this mean? If I have k equals 1 to n, but I just have the letter C, what that means is I can't plug my k into anything, but I will at least count out n of these C's. So for k equals 1, I'll have C. For k equals 2, I'll have C. For k equals 3, I'll have C. You get the idea. This will go on until I get to k equals n. So this is a total of n terms. So the formula then, k equals 1 to n of just the number C, is C times n. I won't usually develop many of these formulas. You can look in your textbook for the development of them, but this particular one is a famous story that I figured we might as well I might as well tell you about it to show you how the formula is derived. So if I wanted to add from 1 to 100, you could. This is one way you could do it. You would have 1, k equals 1, then k equals 2, then k equals 3, then k equals 4, and this would go all the way up until you got to 100. That's one way to look at it. One of the most famous mathematicians ever, his name was Gauss, was a brilliant mathematician who very early in his life figured out a much faster way of adding up these numbers. What he did is he rearranged them. So for example, he put 1 and 100 together. So he took the first and the last and combined them. Then he took the second and the second to last, and then the third and third from the last, fourth and fourth from the last, and kept going and going and going until he finally ended up at 50 plus 51. What he noticed that in every single situation, the sum was 101. All the way down until the last pair. Well, how many of these equations, how many of these 101s do you have? Well, there's a total of 1, 2, 3, 4, 50 equations. So this equals 50 times 101. Now, that's not quite the formula, but that's what works here. I'm going to rewrite it in the way the formula appears. This is the formula in which it appears. This is the way that we would use the formula. In that, I mean that if I get the sum from k equals 1 to n of just the letter k, that equals n times n plus 1 over 2. The sum from 1 to 100 of k squared, that's going to equal 1 plus 4 plus 9 plus 16 plus 25. That's going to keep going and going and going until you get to 100 squared, which is 10,000. Now check this out. You can check it out on your own, but the formula says that this equals 100 times 101 times 201, all of that divided by 6. I'm not going to go through the effort of proving the formula, other than to tell you that the formula looks like this. If k equals 1 to n, you're doing k squared. The formula says that you do n times n plus 1 times 2n plus 1 all over 6. And let me check just to make sure. In this case, the n here, which is on top of the sigma, is 100. So I have 100, that would be my n. Then I have 101, that would be my n plus 1. Then 201 would be 2n plus 1, 2 times 100 plus 1. Those formulas that I came up with there are going to be the three most important formulas, because what I'll require is not going to be more than that. We're going to start using this when we start looking at integrals, but I'll only have you do a select few of these because they're computational and they're heavy. Not really heavy, but they're time consuming. Summation k equals 1 to 45 of just the letter k. If I have just the letter k, I'm going to use this formula, n times n plus 1 over 2. So this is going to equal 45 times 46 divided by 2. I'll let you give the value of it later on. Summation k equals 1 to 50. 5k minus 1. And this is one of the things I wanted to show you as well. You can break this up in the following format. You can do k equals 1 to 50 of 5k minus, and then you can do k equals 1 to 50 of the number 1. You can even go farther than that. Think about this. This is 5 plus 10 plus 15 plus 20. You can factor a 5 out of every single term, so you're able to factor it out of the sum. So according to my formulas then, the formula for k, we have 5 times 50 times 51 over 2 minus, and then this 1 is the c, so I'll have 50 times 1. And once again, I'll let you go ahead and come up with these values. Let's do k equals 1 to 75 of 2k squared. And I'll be able to do what I did before. I'll be able to factor this 2 out front. And then I'll be able to use the formula for k squared. That's n times n plus 1 times 2n plus 1 all over 6. For this one, I'm using a different letter just purposefully, not to fool you or anything like that, but I'm using the letter just to show you we can use other letters. So what I'm going to do, first thing I'm going to do is break this up into 2/3 m plus k equal, I will slip into k myself, but I don't mean to do that if that's not the right letter. And then I'll have 2/3. Now what I can do in order to use the formulas is I can factor this 2/3 out front. And I can do the same thing over here as well. And then I can make use of the formulas. Formula for this one is n times n plus 1 over 2. So I would have 60 times 61 over 2 plus 2/3 times, and this will be m times 1, so just m. It's like 2.m, but it's not supposed to be that way. Summation n equals 1 to 50 n squared plus n minus 2. You could break up into the sum n equals 1 to 50 of n squared plus summation n equals 1 to 50 n minus 2 times the summation from n equals 1 to 50 of n. Nope, that was 1. Okay, so for the first collection here, I'll use the formula for n squared, or k squared, or whatever it was. So that'd be 50 times 51 times, now 2 times this plus 1 would be 201, not be 101, all over 6, plus, now here, for this portion of it, I'll have n times n plus 1 over 2, or, well, 50 times 50 plus 1, so 50 times 51 over 2, finally, minus 2 times 50. One last one to seal the deal. Summation k equals 1 to n. This time I'm not giving you the n. Negative 3k squared minus 4k plus 9. I'll do exactly what I did before. I'm going to break this up. K equals 1 to n. Negative 3k squared plus the summation k equals 1 to n. Negative 4k plus the summation k equals 1 to n of 9. Now I'll do like I did with the other ones. I'm going to factor out these coefficients. This will be negative 3 times the sum k equals 1 to n of k squared minus 4 times the sum k equals 1 to n k plus 9 times the sum k equals 1 to n of 1. Okay, the k squared formula, we have negative 3 times, I'll end up with n times n plus 1 times 2n plus 1 over 6 minus 4 times n plus 1 over 2 plus 9n. And then finally, I wanted to do some examples of the types of things you'll face in the next section. And that will be limits of this form. The limit, as n goes to infinity, the summation k equals 1 to n, 5 times k over n squared minus 3 times k over n plus 1, and all this stuff is multiplied by 9 over n. Now, what I typically do in these types of problems is I do break them up into pieces. This n goes to infinity business we're going to do as a very last step. We're going to do all the algebraic stuff first. Well, I'm going to multiply this 9 over n through. And I'll explain what I did in just a minute. I took the 9 over n, multiplied to the first part, and you know what? I didn't actually do the 9, did I? This has to be a 45. And this right here will be a 27. So give me a second to regroup. When I take the 9 and multiply it through, I'll get the 45, I'll get 27, and I'll get 9. There's 45, 27, and 9. This is k squared over n squared. If I multiply by 1 over n, I'll get k squared over n cubed. Similarly, I'll have a k over n squared because of this n. And then finally, 1 over n. Now here's how I'm going to use the formulas. I'm going to break it up into 3 sums. So I'm going to do something like this. I'll do k equals 1 to n of a 45 times k squared over n cubed minus the summation k equals 1 to n 27 times k over n squared plus the summation k equals 1 to n 9 over n. Now, you have to understand in each of these, the variable is k. N is the number they're going to, so n is not a part of the counting. This n cubed will be the same whether k is 1, 2, 3, whatever. So I can go a little bit further in how I broke things up. In the first one, I can factor out 45 over n cubed. And what I leave behind then, k equals 1 to n, will just be k squared. That's the only variable is k, so I only need to leave k behind. Same thing over here. 27 over n squared is like a constant multiple. So I'll bring it out front of that particular sum. K equals 1 to n of k. And then finally I can pull this 9 over n in front of this last sum. 9 over n times the summation k equals 1 to n of 1. Now I can use the formulas. So I have 45 over n cubed. The formula for the k squared was n times n plus 1 times 2n plus 1 divided by 6. The next one was, we had minus 27 over n squared. The formula for k equals 1 to n, is n times n plus 1 over 2. And then finally, this last one is just n. 9 over n times n. Now, a lot of simplifying can happen here, and I'll show you how. If you are sneaky enough, you can really make this work fine, and I'll show you how. What I'm going to do first of all, of course, is divide here into here. I can take a 3 out, so I'm going to have 15. So let me pull the 15 over 2 out. You'll notice I can take out an n here, but I can also, you may not know this, I have n squared left over. I can write this part as n plus 1 over n times n 2n plus 1 over n. See, there's my n squared down there. Minus 27. Now, over 2, pull the numbers in front here. I can cancel an n like I did before, but what's left is n plus 1 over n. And the last one, the n's cancel, and I'll have plus 9. Check this out then. 15 over 2 times, this part right here I'm going to rewrite as 1 plus 1 over n. And this part here I'm going to rewrite as 2 plus 1 over n. I'm going to do the same thing on the second piece. 27 over 2 times 1 plus 1 over n plus 9. Now, I'm going to let n go to infinity. That's finally what I'm going to do at this stage. 15 over 2 is untouched by that, but this part right here, this piece right here, will go to 1 plus 0, because the limit, as n goes to infinity of 1 over n, is 0. Just like 1 over x. Same thing happens here. I'll have 2 plus 0 minus 27 over 2 times 1 plus 0 plus 9. Notice how I've not written the limit again because I've now taken the limits. And let's see if I can do some simplifying. I noticed here that this 2 will cancel with that, and I have 15. Nothing cancels here, so I have negative 27 over 2 plus 9. So let me see what I have. 15 plus 9 is 24. That's 48 over 2 minus 27 over 2. That's 21 over 2. Let's try another one. Let's try the limit as n goes to infinity of the summation k equals 1 to n, (7) times k over n squared minus 3 times k over n plus 4. Times 1 over n. So I'm going to do exactly what I did last time. The limit as n goes to infinity brackets 7 over n cubed times the sum k equals 1 to n k squared. I'm doing everything in one shot. See if you can follow along. Minus 3 over n squared times summation k equals 1 to n of k plus 4 over n. Not so fast. Plus 4 times the sum k equals 1 to n of k. That'll be 4 over n. Alright, I think I got everything. This equals the limit as n goes to infinity 7 over n cubed times n plus 1 times 2n plus 1 divided by 6 minus 3 over n squared times n plus 1 over 2 plus 4 over n times n. I'll play the same exact game I did last time. I'm going to take and make that a square and take that n out. I'm going to take out an n here, and I'll take these n's out. And I'm also going to suck the two n's into each of these two terms. So I'll have the limit as n goes to infinity. I'll have 7 over 6. N plus 1 over n is 1 plus 1 over n. 2n plus 1 over n is 2 plus 1 over n. Minus 3 halves times 1 plus 1 over n plus 4. And now I'm ready to do limits. All these 1 over n's become zeros. So that's 7/6 times 1 plus 0 times 2 plus 0 minus 3 halves times 1 plus 0 plus 4. So this 2 and this 6 I can cancel a little bit. I have 7/3 minus 3 halves plus 4. Get a common denominator of 6. So 42 over 18, common denominator of 6, not 18. I'll get 14 over 6 minus 9 over 6 plus 24 over 6. And I'll have 38 minus 9 will be 29 over 6. And one last one. Limit as n goes to infinity, summation k equals 1 to n. 11 minus 3 times k over n, and that's times 4 over n. So as before, I'm going to try to do it all in one fell swoop. I'll explain what I did though. Took the 11 times 4 over n, and I got 44 over n. There was no k, so I could bring that all in front of the summation sign. So for this one here, I had the 3 and the 4 gave me the 12. There was a k hanging around the numerator. N times n gave me the n squared. So this is the limit as n goes to infinity. 44 over n times n minus 12 over n squared times n plus 1 over 2. Cancel these n's. And you'll just get a 44 for that part. Here I can cancel an n before, then don't forget to suck the other n underneath of the n plus 1. 12 and 2, I can get a 6 out of that, so I have minus 6 times 1 plus 1 over n. 44 is unaffected by the limit, so we have 44 minus 6 times 1 plus 0. And that equals 38.